Thanks for inviting me. Hope everyone is awake. It's an exciting afternoon. So let's get started. So hi, that's me. I'm an assistant professor at the University of Amsterdam. I mostly work on self-supervised and multimodal learning, but also a bit of work on privacy and bias recently and causality. I can find more works on my webpage. So I'm going to actually start with a very brief introduction to self-supervised learning. So first of all, why do we want to do self-supervised learning? And I'm going to keep it a bit short because I know everyone is quite an expert here. So I'm just going to give you two reasons mainly. The first reason is the scalability. So we know Instagram has, for example, 50 billion images and counting. And the stuff we're using nowadays to train most vision models is ImageNet. ImageNet is 1 million images. So we can visualize this. And ImageNet has 1 million images. The typical split we use, the 2012 split, is in the middle row. And you can see 1 billion is already quite a bit more. And now Instagram has 50 times that, if not more. So if you think about annotating this, even Elon Musk will run out of money. So if you want to learn from a diverse set of data, you basically have to go self-supervised, or weakly supervised is also a case. But in this case, you're using the signal that's from the raw data. And that's what we want in self-supervised learning. Now, besides the scalability that you can work on much bigger data sets, which of course works better in terms of diversity. So the inputs you will see are more diverse, etc. There's some more reasons. So of course, imagine if your concepts keep on moving, then you have to constantly relabel unless you talking about Eastern European cars. Of course, once pre-trained, or you can pre-train all kinds of data sets, including medical, where you might not easily get labeled annotated data. Of course, labels also carry a lot of problems, like what even is a house, and the same actually goes for text-image data sets like CLIP, which can be highly biased. You don't have that as much with self-supervised learning. And finally, simply studying what you can learn from images alone is a really fundamental problem, and as such is quite interesting as a research question. Before I go into the research, I want to give one note about the pre-training data sets also related to this bias. So most people at the moment use ImageNet for pre-training self-supervised models, which if you think about it, doesn't really make all that much sense because ImageNet is class balanced. It has classes, and notably 120 classes of dogs. It's object-centric, so it's not really representative of the world we have. So if you ever think about training something in that direction, I recommend this recent data set that we put out called PASS, which is a data set specifically for pre-training self-supervised representations and has actual licenses, not like ImageNet. So you can actually use these images, and importantly, it protects GDPR by not including any people or otherwise identifiable information, which, as it turns out, is completely fine if you're doing self-supervised pre-training, because all you're doing is learning features. All right, so since it's only 15 minutes and I've spoken 5 minutes, let's go into the actual research. So I'm going to talk about a method of ours which learns generalizable representation, and as such basically gives you a free labeling of images, where we use optimal transport for self-supervised learning. The paper is called Self-Labeling via Simultaneous Clustering and Representation Learning, and was a spotlight at ICLR 20. And I'll show you at the end why it's still relevant despite its being old in quotation marks. So we start with the main idea of self-supervised learning, right? So if this is our image data set, or rather more like something like this, and then you times this by 50 and you roughly end up at ImageNet size. So you can immediately see again why labeling might be a bad idea in general. And now what we want to achieve is we want to group these images by concepts. So we call them concepts, you can call them clusters, we call them also self-labels. And the question is how to get from here to there. And of course, in the usual context, it's quite easy, where you start with a strong model, for example, and then you pseudo-label your images. Or you start with a labeled data set and you get your model that you train on these labels. So this is really a chicken and egg problem. And the question is, can we somehow solve this chicken and egg problem simply using self-supervision? And the main idea, what we're doing here is, and common to all of self-supervised learning, is we're going to use augmentations. Augmentations such as different lighting or mirroring or zooming in, they all keep the same meaning of the image. And we're going to use this prior knowledge to train the networks to respect this, basically. So how does it work on a high-level idea? We first start by assigning each image a random label, for example, like this. And then we check if the augmented version of these images also contain the same label. And in this case, the model gets it wrong. And so what we are going to do is we're going to make the assignments consistent in such a manner that you can now say that image 1 belongs to label A, and image 2 belongs to label 2. Now, on a mathematical level, you can read the paper, of course. What we simply do is we're relaxing the normal cross entropy laws to be optimizable. So we're going to be optimizing this Y in a not one hot manner, but in a soft manner. And if you do this in a soft manner, you quickly run into trouble because you get some trivial solutions which you don't want. And what we did here, we solved this basically using some sort of regularization, which, as it turns out, can be posed as optimal transport, for which the mathematician and machine learner Couturi has some amazing papers on, which you can actually solve extremely quickly using matrix multiplies, which of course is exactly what GPUs love. So we put that out there, and the overall, we use this to basically make these assignment consistent. And so the overall algorithm looks as follows. You start with your randomly initialized neural network, in this case a CNN. You apply this optimal labeling procedure, which uses optimal transport, and you get some label assignments. Now, these won't be perfect at the beginning, but they will be good enough. You then train your network with cross-entropy training while using these augmentations, then your model gets slightly better. And then again, you do this optimal assignment and you keep on going. It's kind of like an expectation maximization algorithm in that sense. And with this algorithm, we basically solve the age-old mystery of what comes first, whether it's the chicken or the egg. And it is the chicken, and more accurately, it's a randomly initialized chicken. So let's take a look at some qualitative results. We can take ImageNet and simply look at what kind of concepts or clusters some images belong to. So for example, these images have all been found to belong to one particular cluster. And of course, we can recognize it as the concept or the cluster of a geyser. And similarly for the zebra cluster or the butterfly cluster and the ball of hay cluster, because why not? And actually, because ImageNet happens to be a labeled data set, again, there's no reason why like our method is self-supervised, so you could apply it on everything. But we can now check actually, does it match what people have labeled this data set with? So now we're going to, as you can see on the right, we're going to add a border color around these images, which depict the ground truth class as humans have labeled it. And you can see here that it matches pretty well. Of course, this is somewhat cherry-picked. It's not the case for all the images. However, we've released all of the clusters online. And if you were to go through this and click on one of the clusters, which, for example, have a low purity value in terms of ImageNet classes, you still find very interpretable features. For example, you would find humans walking in a forest, and sometimes the ImageNet class would be dog because they're walking a dog. Sometimes it would be bicycle because they're riding a bicycle, but it would still be quite interpretable, actually. Right, as I teased it that it's still relevant. And for example, by simply updating the augmentations, it works better than SimClear, even though everyone knows SimClear. But if you simply use the same kind of augmentation, it ends up working better, and of course, training longer and so on. Swath from Facebook is basically, or is actually doing synchron-knop, this optimal assignment algorithm in an online manner. And then finally, you might have heard about the method Dino, also from Facebook, which is essentially doing synchron-knop optimal transport, except they're, instead of using the matrix multiply, they're using a centering operation. So you can still find the same algorithm working in these various kinds of self-supervised learning setups. Now, to conclude sort of from this paper, we have these three ideas. One is the invariance to augmentations as a free learning signal. And that's what we use for bootstrapping the self-supervised learning. Secondly, we have this idea of labeling and representation learning. Labels are very useful because similar to supervised labels, they contain a lot of information, and we can use them to analyze how the network sees the data, basically. And finally, this idea of balanced pseudo-labeling, which is well-defined, a fast objective, and has been used for various other topics as well. Now, this was on ImageNet, pre-trained at the time, because we didn't have the data set back then. However, we're sort of waking up to the fact that the world is not object-centric. The world looks a bit messier like this. And depicted are, for example, the center of the bounding boxes on these data sets. You can see that ImageNet, basically every object is exactly in the middle. But we want to go towards more in-the-wild data sets like a robot would encounter. So I'm just going to tease you one paper here, which we published at CVPR 2022, where we basically do self-supervised segmentation. So all of these segmentation maps are generated self-supervisedly. You can see the people all have the same color, etc. And it's really like self-supervised learning is really moving beyond the image level to the dense domain at the moment. This method is called Leopard, and yeah, Adrian was a master student of mine. And then you can also take the same method actually and use it for multimodal learning. So for example, if you have a video like this with a sound, I'm not sure if you can hear it, but you heard the sound and you hear this sound, 2 times the sawing sound. The images might look very, very different, but the sounds are really almost the same. So you can use this similarity to actually learn that actually the images are also the same. And similarly, you can do it with when the visuals are the same, in this case, a very particular piano keys and 2 different sounds, like classic piano and a very hip e-piano. You can use it vice versa to use these as learning signals. And so this is another paper of ours, which we published at NeurIPS, which is basically doing clustering on multimodal data, in this case, audio and video. 40 seconds left. So finally, you can also, again, visualize the clusters. So for example, it finds this cluster of playing harp or these other clusters of yeah, fireworks, hockey game, vehicle driving. Of course, we just named these clusters because everything is self-supervised here. And again, we released everything open source. So the conclusion is, I gave you a bunch of reasons for self-supervised learning. I showed you that self-supervised learning, especially with synchron knop and optimal transport, can be used for all kinds of things, can be used for dense self-supervised segmentation, as well as for multimodal clustering. All right.